I'm going to introduce the sine, cosine, and tangent functions. All right? Before I do, I'd like you to do a small exercise with me. So on a piece of scratch paper with a ruler, as best as you can, I'd like you to draw 3 right triangles as follows. First, draw a fairly large right triangle with a vertical and horizontal leg. Now, then draw 2 other right triangles also with vertical and horizontal legs, such that all the right triangles have the same left vertex and the same left angle measure. All right? So your drawing should basically look something like my drawing. All right? Your left angle measure is likely different than my left angle measure. Likewise with your top angle measure for each triangle. That's perfectly fine. That's not important. Okay? I'm going to call my left angle measure theta. And notice that theta is the left angle measure for all 3 overlapping right triangles. All right? So pause the video now and finish that drawing if necessary. Okay, now I will continue. So would you also now please measure the lengths of all the sides of all the triangles? All right, so I would recommend using a metric ruler with millimeter markings. That'll probably be the most convenient to take accurate measurements. All right, so when you're done, you should have 9 measurements. You should have 9 hypotenuse lengths, 9 vertical leg lengths, and 9 horizontal leg lengths. So go ahead and pause the video and do that now, please. Okay, so I'm going to continue. So I'll assume that you have your 9 measurements. Now, for each triangle, I hope you agree that they all have the same left angle measure theta, and they all have vertical legs. Let me refer to the vertical legs of each triangle as the opposite leg. Okay? Now, the reason I'm calling the vertical legs the opposite legs is that those legs are the farthest legs from the left angle. Okay? And let me call the horizontal legs the adjacent legs, because those are, well, they're adjacent to the left angle. Okay? And then the hypotenuse, of course, is the hypotenuse. All right, so I've labeled the sides of the small triangle, but obviously all 3 right triangles have a hypotenuse, have an opposite leg, and an adjacent leg relative to the left angle. Okay? Now, here is the interesting thing that the Greeks discovered a long time ago. For each right triangle, if you measure the ratio of the opposite leg length to the hypotenuse leg length, you'll notice they're approximately all equal. The same thing is true for these other 2 ratios. The adjacent leg length to the hypotenuse leg length and the opposite leg length to the adjacent leg length. Okay, so if that wasn't clear what I said, I'll make up some numbers to make this more concrete. Okay, so let's suppose that my smallest triangle had lengths 3 centimeters and 4 centimeters, and let's say my hypotenuse had a length 5, okay? And let's say that the largest triangle had a opposite leg length 6, and or how about, actually, let's go with 9. 9 is probably closer to what it actually is. Okay, and then let's say that the adjacent length for the largest triangle was 12. Okay, and then for the middle, maybe we'll say that this length, the middle right triangle, maybe the vertical leg length is 6, and maybe the adjacent leg length is 8. Okay, and then also for the hypotenuses, let's say that the hypotenuses have lengths 5, 10, and 15. Okay, so the opposite over the hypotenuse for the smallest triangle, for my smallest triangle, I have 3 over 5. For the middle triangle, I have 6 over 10. For the largest triangle, I have 9 over 15. For the adjacent over the hypotenuse, for my smallest triangle, I have a ratio 4 over 5. For the middle right triangle, I have a ratio of 8 over 10. And for the largest right triangle, for the corresponding ratio, I have 12 over 15. And then for the opposite over adjacent, for my smallest triangle, I have the ratio 3 over 4. For the middle triangle, 6 over 8. And for the biggest triangle, 9 over 12. Now, your numbers are not going to be are not all going to be integers. You're going to have decimals, and then your fractions, you can turn your fractions into decimals with a calculator. So what I'd like you to do is find now all your 9 corresponding ratios. Okay, you will see that all 3 ratios for all three triangles, the opposite over hypotenuse ratios, are all going to be approximately equal. Also, your adjacent over hypotenuse ratios are all going to be approximately equal. Okay, and your opposite over adjacent ratios for all 3 triangles are going to be approximately equal. Okay, so pause the video now and convince yourself that that is true. Go ahead and take your measurements, use your calculator to find the decimal approximations to these ratios and compare them. Okay, so do that now. Okay, so now I will continue. So notice something interesting. Apparently, the size of the right triangle is not so important, is it, as far as these ratios are concerned? The only thing that's important is that this left angle measure is the same. I have 3 different right triangles, but because they all have the same left angle measure, and they also have vertical and horizontal legs, apparently they all have these ratios in common. Okay? Now, this is a big deal, and this is very useful. All right? We have names for these ratios. Okay? The opposite over hypotenuse, that's called the sine ratio, or the sine function. It's a function of theta. Okay? So the way that we would write it is Sin, that represents the sine function, Sine. So the sine of theta, that function is equal to this ratio. All right? The cosine, Cosine, the cosine function of theta is written this way, and that's equal to the adjacent over hypotenuse ratio. And the tangent function, tangent of theta, that's the name given to the opposite over adjacent ratio. Okay? So the only thing that is important is what the left angle measure is. All right? The other details of the triangle, the size of the right triangle, that's not important. Okay? We're going to be using the sine, cosine, and tangent angles very much in this class. So you're definitely going to want to familiarize yourself with these definitions. Okay? Now, let me show you an example of why you would care that these ratios are the same for all triangles with the same left angle measure. All right? So suppose that you were tasked with finding the height of a skyscraper. How in the world would you measure the height of a skyscraper? Okay, well, you could obviously get a crane and lay a long ruler along the side of the skyscraper, right? Of course, that would be impractical. Okay, can I show you an easier way that simply uses the wonderful functions that we've just defined? Okay? Now, during the day, the sun is going to shine on the skyscraper, and the skyscraper is going to have a shadow. Let's say that the sun, let me draw a ray. Let's say the sun shines there. Let's say that one ray looks like this. And let's say that we've got the shadow of the skyscraper right here, with this length. All right? Now, what if at the exact same point in time you put a meter stick on the ground, exactly vertical? All right? So the sun is going to shine on your meter stick, and a ray is going to have the same angle with the ground as the ray that touches the top of the skyscraper. Okay? And so your meter stick is also going to have a shadow of some length. Now let me put in some numbers just to make this more concrete. So you have a meter stick, so the vertical leg length is 1 meter. And let's say that your shadow was 0.4 meters. All right? Now, measuring the height of the skyscraper is not easy. However, measuring the length of the shadow is a lot easier. Okay? Let's say that you measured the length of the skyscraper shadow at the same point in time. And let's say that it was 40 meters. All right? Now, with that information, you can calculate the height of the skyscraper without having to risk breaking your neck, climbing a large ladder or using a crane or something. All right? So why is that? Well, watch this. The light ray is making a left angle theta with the ground. We don't know what theta is, but we know that the meter stick and the skyscraper light rays are creating the same angle. All right? We also know that the tangent function, tangent of theta, is going to equal a certain ratio. It's going to equal the ratio of the vertical leg length to the horizontal leg length for each of the right triangles in my drawings. All right? Now, why is that? Well, we just did a lab to convince ourselves that if you have right triangles with the same left angle measure, that these ratios will be the same. So what I'm saying is that 1 over 0.4 is going to be the same as our mystery height divided by 40. Okay? Now we have an algebra equation. We can cross multiply and solve for h. Okay, so 1 times 40 equals 0.4 times h. So h is equal to 40 divided by 0.4, or 400 divided by 4, or 100 meters. Isn't that cool? So using the properties of one of the functions we've just defined, we just made our lives easier. All right? And there's going to be lots of other useful applications, but this just gives you a sense of why these functions are wonderful.